using the quadratic formula. What is the quadratic formula? What is it used for? When you have a quadratic equation in standard form, ax squared plus bx plus c equals 0, and you're asked to solve this quadratic equation for x. The quadratic formula is a strategy for determining the solutions to the equation. Often there will be two solutions. In some cases there'll be one, in other cases no solutions. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we'll get some practice using this formula. Here we're asked to solve the equation x squared minus 9x plus 20 equals 0. Now we have other strategies for solving this quadratic equation. We could factor it. We could complete the square. But let's get practice with the quadratic formula. Since it's in standard form, a, b, and c are relatively straightforward. And the formula we'll write down. When we substitute in our a, b, and our c, we'll remember that negative b really means the opposite of b. So the opposite of negative 9 is 9, plus or minus the square root of. Under the radical, it will become 81 minus 80, or 1. And the square root of 1 is 1. So our two solutions will be 9 plus 1 divided by 2, or 9 minus 1 divided by 2. So 10 divided by 2 is 5. 8 divided by 2 is 4. Okay, now the picture of this. If I were to graph the related quadratic function, f of x equals x squared minus 9x plus 20, the curve would go through the x-axis at 4 and 5. So here's an example where the quadratic equation is not in standard form. Our first step is to rewrite it. Let's identify our a, b, and c. We'll write our quadratic formula and substitute in our values. So this becomes the opposite of negative 18, or 18, plus or minus the square root of 324 minus 128 all over 2. Underneath the radical, we have the number 196, which is a perfect square, so that makes it nice. Our two solutions will be 18 plus 14 divided by 2, or 18 minus 14 divided by 2. So notice this was a pretty clean process when the number underneath the radical is a perfect square. So what happens if, when I substitute in my values into my quadratic formula, I don't get a perfect square under the radical? That's the case of having what's called irrational roots. So here's our quadratic equation. It is in standard form. A is 5, b is negative 3, and c is negative 1. So we can substitute everything into the quadratic formula. But here we see an example of what happens when the radicand is not a perfect square. So if we're asked to approximate these solutions, we need a calculator at this point. And we'll do 3 plus the square root of 29 divided by 10, and 3 minus the square root of 29 divided by 10. So we have one positive and one negative root, both pretty close to 0, right? Less than 1 unit away from 0. So to verify that, one of my favorite apps is desmos.com. It's the graphing calculator tool. You can type in y equals, or f of x equals 5x squared minus 3x minus 1 and hit graph. And then if you hover over where the graph crosses the x-axis, Desmos will tell you what those roots are, rounded to the nearest thousandth. So we can verify that the work that we did with the quadratic formula was correct, and these roots are irrational. Okay, will there ever be a case where there's no solution? And how do we determine that from the quadratic formula? Well, here we have a quadratic equation in standard form. A is 2, B is 3, and C is 4. So we can use our quadratic formula and substitute in our values and simplify. But notice underneath the radical is a negative. There is no real number, which is the square root of negative 23. Therefore, there are no real solutions for this quadratic equation. So it's always good to have a graphical picture of what this looks like. If we use Desmos again and typed in, f of x equals 2x squared plus 3x plus 4, and we graphed that, we would notice that the graph does not go through the x-axis. That's how we know there are no real solutions. Okay, finally, a contextual problem. This is a common context for a quadratic function. From an initial height, s, of 70 meters in a stadium, Lewis tosses a ball up at an initial velocity v of 5 meters per second. Use the equation negative 4.9 t squared plus vt plus s equals 0 to find the time t when the ball hits the ground. So you know the way a ball, when it's thrown up into the air, it follows a curve that looks like a quadratic function, right? And in this case, our dependent variable is time, and our independent variable is the height. So we're going to use the quadratic formula, but instead of x equals, it's going to say t equals, right? And now we'll just substitute in the values for a, b, and c. And we're also going to understand that b in this case is 5 because of the initial velocity was given. And c in this case is 70. Excuse me, yes, c is 70. So here are our values that are substituted in. Now we'll need a calculator, right? These numbers are messy. And we end up with two solutions. But as is often the case with contextual problems, one of the solutions will be eliminated because it won't make sense in the context. It doesn't make sense to have a negative 3 seconds, right, for time. So after approximately 4.3 seconds, the ball will hit the ground, will be the solution to this equation.